Okay, so I'm going to go through this variable frequency drive. I normally do this, obviously, use this PowerPoint in class, but the module itself does go through everything pretty good as far as saying, the specifics. It's pretty heavy in the information, and it's a lot of just written stuff. So a lot of this on this slide is regurgitated right from the module, but definitely use this as a Coles Notes version as well too. So I'll go through this again the best way I can, but knowing that you could easily stop this at any time and read what I have on there. So I'll try not to read verbatim over and over here. The big thing to have an understanding of with VFDs is that there's certain motors that will not work with VFDs and they could get damaged. And they talk about how or why that's an issue throughout this module. Not to mention the cabling as well too. Okay, so there's very specific motors and cabling that we should be using with a VFD. Not all induction motors are going to be suitable, and it can actually burn up the windings, cause arcing at the bearings, and just basically make it so that the shaft won't turn. So basically render the motor useless. So we do have to be careful when we hook motors up to these VFDs that they're rated for such. The big thing again with the VFD, variable frequency drive. So we're varying the frequency of the supply to the motor so that it operates slower or faster. And we can do that with the VFD. So speed considerations. Again, if a standard motor is controlled by a VFD and operated at a slower speed, it may not be properly cooled. A lot of them have fans on them to cool them, so the fan's not turning as fast. They may have specific speeds, even if they are rated, that we can't exceed or go lower than, basically, if that's their rating. So we definitely have to pay attention to that. The voltage spikes, the VFD output can produce voltage spikes higher than the peak of the line. This can damage the winding insulation on the motor itself. So again, it's rated for a certain voltage. If we put voltages that are greater than that, we can damage the motor. Induced voltages, we can get higher carrier frequencies from the VFD, and they'll go into detail of all of these things coming up here, and induces voltage into the shaft of the motor. This can exceed the insulation value of the bearing lubricant and arc across the bearing. So if they arc, they could get welded together and then obviously not allow the motor to spin freely. We can also get circulating currents in the core causing overheating. Obviously overheating is damage and we want to avoid that as well. Motors for use, so what the motors we can use can be induction motors or non-induction. The induction motors I talk about are inverter ready. They have better insulation and thermal capacity, so the heating's not such an issue. Inverter duty, they're again just specifically designed for VFD operation. And vector duty rated, they're like inverter duty motors, but they come complete with shaft encoders to give feedback to the drive about rotor speed and position. So these would be very specific and I assume quite expensive, that you can send a signal back to a computer or PLC or something that's telling the system exactly how fast the motor is going, and then it can make adjustments based on that. So they need to be marked for VFD use. So here's an example of a inverter duty rated motor nameplate right out of your module. So you can see your frequency ranges based on your foot-pounds torque, and then also your maximum RPM, okay, based on those frequencies. So we can see we have a range here, so that tells us that we can vary the speed to this motor. There's also non-induction motors that we can use. Again, they're basically definitions of these permanent magnet motors. They're only meant for operation with a VFD. They do not have a squirrel cage rotor that carries the current to create the necessary rotor magnetic fields. So it's not developing torque in the rotor bars, just like a squirrel cage induction motor. They can be thought of as synchronous motor, which requires virtually no speed difference between the rotor and the rotating field. Okay, so that's just like the synchronous motor we talked about in machines. Wound field brushless excited. Synchronous motors, the speed of synchronous motor is controllable, and the wound field allows for power factor to be changed for power factor correction. So that'd be an advantage. So again, just concentrate on the differences between all these motors in case it comes up as a question. Last one to talk about is reluctance motors. Magnetic reluctance is the effect created by a magnetic field because it likes to concentrate in ferromagnetic material that is more permeable rather than air. Okay, so like a nice iron material, just so we can create a magnetic field. Again, air is more reluctant than metal. If the magnetic field on the stator pole switches to another set of poles, the rotor turns to provide the lowest reluctance path for the poles that are magnetized at that time. Changing the speed at which the stator poles are energized in a sequence changes the speed of the rotor. Okay, so again, just read through that. I won't just read verbatim out of the module here. So the basic operation, this is a formula we've talked about getting our synchronous speed. So that's 120 times the frequency divided by the number of poles. So it's the frequency and the number of the poles that are going to determine the speed. And again, we can't change the number of poles once that's decided. Obviously, that's a set thing without literally manufacturing the motor itself. So the only thing we can do is change the frequency. So if we control the motor by changing the frequency, we can do that by an operator, input from a PLC, feedback from sensors on a monitoring process, just like we talked about previous. And it can be programmed to deliver a frequency between 0, 60 hertz or higher. Okay, so again, we can sit right at this nameplate, this display here, and change the speed manually, or it could be done remotely. Or it could be done from feedback from the motor. Okay, so we'll talk about open and closed loop control here coming up later too. Applications for VFDs that may benefit from the variable speed would be fans, pumps in industry, oil wells, large mining trucks, and phase conversion. So we don't necessarily require a three-phase input. Most accept a single-phase input and can recreate a three-phase output. So we talked about phase converters in third year, and those are kind of getting put to the wayside because we can use VFDs for phase conversion as well now too. And they're becoming a lot cheaper than they were. VFDs were very expensive, when they first came out, but they're obviously more wider used now and becoming a lot cheaper. Some advantages, again, energy savings, reduced noise, reduced maintenance cost, and control flexibility. Those are huge advantages for us to use a VFD over other speed control devices. Some disadvantages though that come with it, we get harmonics. So we have to have special, harmonics is an issue, and we have to have special cabling requirements. Harmonics are frequencies that are superimposed on a power system as a result of nonlinear electric loads such as VFDs. They distort the current and voltage waveforms. This can create problems for electrical systems, extra heat in distribution transformers, torque loss in motors, and disruptive noise in communication systems. That's the harmonic distortion. So we get frequencies that build up on these. We get potentially third harmonics, which will basically triple our frequency, and that causes these issues in our current and voltage waveforms. Again, if we have any distortion of that, we could potentially exceed the values that the motor is actually rated for. So they'll put line reactors on the load and line side to help reduce those. So we want to protect the utility and protect our load. So we'll try and reduce those. So these harmonic frequencies combine with the fundamental frequency to produce peak voltage spikes and flow back into the utility supply lines. Equipment such as UPS, computers, fax machines, lighting systems, and VFDs are sensitive to harmonic distortion and can also be a source. So we have our fundamental frequency. Again, our third harmonic is literally 3 times that. Fifth harmonic would be 5 times that. Okay, but we're getting these frequencies that are going to start affecting our waveforms. And we definitely don't want that. So the supply utility actually specified the total harmonic distortion that they will allow back on their supply lines. So if you buy a VFD, I assume that the line and load reactors are already installed and would be within these ranges. So they say generally a limit of 3% total harmonic distortion is allowed at any distortion above that requires remedial action. Okay, so if it's determined that it is higher than that, we would put filtering on the line side. That's to protect the utility, and again, we would also potentially have it on the load side to protect the motor. So what is a line reactor? It's a large inductor in series with the drive on the line side. Okay, inductors oppose a change in current and suppress the harmonic frequencies before they reach the supply line. So we can do this on the load side as well too. So here's our line reactors here, again protecting our utility, and our load reactors protecting our motor. What's kind of interesting here to see in this first diagram is that this is very similar to our UPS. The only thing we don't have is the DC storage batteries. So we still have a rectifier where we're taking AC down to DC. So now we have a DC going into this DC link section, which is filtering it out, smoothing out our DC to get the most steady state value of DC we can. And then it's going to an inverter and outputting AC back to the motor. But as we talked about in UPS with the pulse width modulation, we can determine the frequency because we're basically creating our own sine wave on the output of that inverter. So we can manipulate the frequency, and that's how we can change it to the supply of the motor. This logic control, again, could be a computer, PLC, feedback from the motor, could be all kinds of things to basically change that. Okay, it could be you sitting right in front of the VFD and manipulating on the control panel as well. Special cabling. Due to the nature of the electrical output of a VFD, special cables may be needed. The cables contain significant values of inductance and capacitance that are directly proportional to the length of the cable and the insulation thickness type. So they talk about the cabling and also the bonding that's in there. So a lot of them in the top graph, you'll see they have 3 separate bonding conductors, and that helps to reduce the frequencies. Basically, they say that the radio frequency can be reduced by having multiple bonds, or they will say that they will have a bonding wire that is the same size as the conductors for the rest of the circuit. So we'll see a large bonding conductor, not what we would commonly see in a regular cable. Again, the cables contain significant values of inductance and capacitance that are directly proportional to the length. The cable run between the motor and the drive is seen as an impedance to the VFD. Whenever cable surge impedance does not match the surge impedance of the motor, a reflected wave occurs. Again, load reactors can be used between the drive and the motor to help reduce this problem. If we don't reduce it, those reflected waves can actually cause high spikes to the motor terminals, which can produce destructive conditions for the insulation. And then we get pitting, and that again is at the expense of the motor. The installation, again, we want to correctly install them. We pay attention to important factors such as environment, the electrical connections, grounding, supply voltages, and protective devices. Over 50% of the drive failures are a result of improper installation and startup, so that's somewhat our responsibility for that. So location to the supply conductor quality is we have to watch out for location, supply line, power quality, bonding, control wiring. And then location, heating again is an issue, leading to it's probably the number one, that's what it says, the leading cause of VFD failure. They are best operated between 10 and 40 degrees Celsius. They should be in locations free from dust, not installed in direct sunlight, hazardous locations. Okay, again, just check through that stuff. Supply line power quality, again, we want to be within 10%, otherwise the device will most likely trip. Bonding, again, here's where it talks about the voltages induced. They must be properly bonded so that the voltages induced in the case and shaft of the motor don't cause arcing in the bearings and result in failure. Bonding rings are sometimes installed on the motor shaft to prevent buildup. And some manufacturers recommend that the bonding conductor size be not less than that of the circuit conductor. So again, that large size. And then sometimes, again, they say 3 bonding conductors are used in some cables to provide extra bonding conductor area to help with reduction of radio frequency interference, or RFI. Control wiring, just said never connect 120 to the control boards of the VFDs, could lead to catastrophic results. Analog signals to and from the drive should be shielded against transient voltage, and the shield should be bonded on one end only to allow for draining any imposed transients. So like our sheath currents. Power wiring, control wires should never be run together. So again, our components. VFDs control the speed of an SEM or synchronous motor by controlling the frequency and voltage. The VFD rectifies the incoming AC power into a pulsating DC wave. So this is not new to us. We have our rectifier. We get pulsating DC coming out. We get filtering action here from our, this would be a L section. We have our choke and capacitor filter. Then we get our clean, smooth DC coming out into our inverter, and then we can manipulate the AC output to the motor itself. So again, very similar to UPS. We just don't have that storage option for our battery section. So the rectifier section, again, changes the AC to DC, most commonly a fixed diode bridge rectifier. Some used an SCR rectifier, so a controlled bridge rectifier, and some use insulated gate bipolar transistors, or IGBTs. Those offer regenerative braking and energy recovery. So the rectifier can be 6 pulse, 12 pulse, or 18. A 6 pulse is basically a 3-phase rectifier. A 12 is 2 full wave bridge rectifiers, but the source voltages are 30 degrees out of phase with each other. The higher number of pulses results in lower harmonics. So here's a picture of our 3-phase full wave bridge that we took in rectifiers and battery chargers. So we're going to see our we're going to see our percentage here that we're going to use. We're going to take our 480, get our peak, and get our VDC output. This is exactly the same that we talked about in the previous modules. So this is the basic voltage output, DC output, again, pulsating DC coming out of our rectifier. What they say is for a 12 pulse, we're going to have the rectifier with 2 secondary windings, so that 30-degree shift. The way we can create that is by having 1 secondary in delta and 1 secondary in Y, and that'll give us our 30-degree shift and give us a 12-pulse rectifier. Now the difference between the 6 and the 12, we can see we have a lot smoother output in the same section here that we did when it was just 6. Okay, so we have basically a smoother DC coming out of there, a less harmonics, and before it's going to the DC link section for filtering. Then the DC link, again, is to filter out any surges or transients on the line power coming into the VFD. Once the pulsating DC reaches a section, it is filtered to provide the steady state. A dynamic braking resistor is often included in this section to dissipate energy from the DC voltage regenerated by a motor decelerating, overhauling. So when the motor decelerating, it can act as a generator and go back into the system. So regeneration may occur in elevators where the motor is used to brake an elevator descent from upper floors. Again, and our inductor, our choke filter in series with the output, our capacitor in parallel to create our L section filter. And the L section is the best for multiple loads. So we're kind of taking advantage of all the filtering by having both of those guys in there. The inverter section, again, converts the DC. Now we're going to get the AC output from the inverter, just like again in a UPS. This section with control logic controls the frequency and the voltage output. It uses pulse width modulation to convert AC from the DC. Various semiconductor switching devices may be used, but the most common is an IGBT. It can provide the high switching speed that is needed for pulse width modulation inverter operation. They can switch on and off several thousand times per second and are very reliable. So again, when we get those pulses that we're creating our sine wave, the output, mimicking our sine wave output, we need to be able to switch that, again, incredibly fast, because we're talking about one cycle within, a 60 cycles in 1 second. So when a positive voltage is applied to the gate from the control logic circuit, the IGBT turns on and current flows between the emitter and collector. To turn it off, the voltage is removed. So that's all you're really going to have to know about the theory of the IGBT. When it is switched on, again, for a short time, it only allows a small amount of current, then it's switched off, and then switched on and left progressively longer. This, again, is our pulse width modulation. Going to get a higher value of voltage and current if we leave it on for longer. So we're switching it on for longer when we want our peak. And then as we decrease back down to 0 or increase from 0 up to peak, we're going to have it on for less. Okay, just like we talked about in UPS. So then it talks about your basic pulse width modulation. So it's showing us our circuit. This microprocessor provides the control logic that controls the switching. Both the microprocessor in the control logic board and the method of programming the control circuit produce the required output, and may be different between manufacturers. So again, this is the control logic that's basically telling these guys when to switch, how long to stay on, depending on whatever output we need. Okay, so again, that's happening very, very fast. That's why we're using solid state switching. Then they talk about the volts per hertz control. The volts per hertz pulse width modulation control technique is the most common and lowest cost configuration. It works well with a wide range of motors, highly reliable, and reflects the least amount of harmonics back to the source. So the volts per hertz control requires the voltage to change and maintain constant at constant ratio. So for a 460 volt motor, the ratio is follows. So if I have 60 hertz, this is how many volts I have per hertz. To achieve 10% motor speed, we need 10% of the frequency, or 6 hertz. So if we're going to have 6 hertz, the amount of voltage that we have based on that ratio is 45.66 volts to maintain that ratio. If the ratio is maintained, the motor will see constant torque and current at the reduced speed. If not, we could see excessive damaging current. So what we want to do is basically maintain this volts per hertz ratio, and you guys will definitely have to calculate that in some questions we have coming up. But again, 10% is what it asks for. It could ask for 50% of the motor. Again, we would just take 50% of the frequency and then times that by the volts per hertz ratio and get the expected output voltage to properly maintain that ratio. Again, think of these diagrams here in the same length of time, same period. So if we have a longer wavelength, we have lower frequency. Narrow pulse width, we're going to get a lower value of voltage coming out of there. If we have wider pulses, we're going to see them switching, the IGBT switching on for longer, and we're going to see a higher value of voltage. And we'll have a shorter wavelength at a higher frequency. So this is just talking about the voltage, what's happening to the voltage when we manipulate that frequency. Flux vector control, it's an improvement on the volts per hertz design. It uses methods to control the stator and rotor flux angles to optimize motor operation. The speed control is more exact under changing load conditions. So again, things can happen with your motor. You can load it up, take the load off, and this technology is way better at adjusting for that because it uses mathematical algorithms to adjust the frequency and voltage based on the phase angle. So flux vector control logic separates the in phase, so the torque. Again, think of our phasor diagram on the in phase component, and the out of phase, or the flux, the magnetic portion of current. Components are individually adjusted to produce optimum torque for maximum speed. This is controlling in the flux vector. So think about our vector diagrams when you're referring to this as well too. Again, I would say probably a higher cost with this as well too, but definitely a better way of doing it. The keypad on the VFD is where we can enter the specific parameters required. You can make changes on the fly if it's on this local control. Local meaning we're touching the screen that's right attached to it. Remote meaning it's happening from somewhere else. Things such as rated motor voltage, current, frequency, maximum frequency, minimum frequency, max speed, minimum speed, all that can be entered in there. A standard VFD can have up to 40 parameters. The flux vector usually requires more. It could have up to hundreds. Okay, so again, way more specific control, but again, I would assume the cost would be quite a bit more in that aspect as well. So then we start talking about different types of control. Open loop control does not have feedback about its status, so we would just program it in and let it do what it needs to do. How effectively the system does its jobs is based on the initial programming. VFD runs at a speed according to a set point or parameter programmed by an operator, or either locally or remotely. Okay, so we set our set points, we get our output, and then we do send that to our motor. Okay, that's the open loop control. So no feedback, just programmed and away she goes. Closed loop control has direct inputs from sensors that lets the system adjust for changing conditions. So now it has feedback. That's the big thing, is it has feedback from the motor back to the control logic so it can make changes on the fly. Closed loop VFD speed control uses direct feedback again, and it's right from the shaft, the exact speed, so it's very precise. Again, a little bit more involved with that, but you're getting a lot more specific operation out of that motor. Proportional integral derivative control, so PIDs. If you've worked, I've done some instrument and some skids, so we definitely saw a lot of PIDs, not knowing exactly what they were at the time, just hooking them up. Accurate closed loop control is provided by PID settings in some VFD control logic. The difference between the measured value and the set point in the controller is called the error. the controller wants to get rid of the error and makes adjustments to make the two values equal. So that's how it's taking that feedback and adjusting to that set point. So the PID control can bring the speed of a motor to its set point as it responds to a change in load or a change in set point very rapidly without overshooting the targeted speed, then maintain that speed. So giving us very specific speed control, okay, with this. But again, we're adding a lot more to this. It's going to be a lot more specific, but a lot more costly and a lot more involved. The feedback from the sensor on the shaft motor is essential for this closed loop because it needs to know exactly how fast that's going. Dynamic braking, whenever a motor is spinning faster than the speed it should be turning, it becomes a generator or is regenerating. The overvoltage produced by this regeneration can be harmful to the DC link section of the VFD if this energy needs to be dissipated. One way of doing this is connecting the motor to a resistor to dissipate the energy as heat. So here's our dynamic braking resistor right here before it goes to the DC link section so it doesn't damage it. So this resistor puts an electrical load on the motor when it's acting like a generator. Okay, so just giving it a path to discharge, if you will. This causes the motor to slow down. To control the amount of braking, the current through the resistor is controlled by a transistor. So this guy right here. Dynamic braking works best when the motor has a lot of spinning inertia at a high rate of speed. If the speed is low, dynamic braking may not work as required. Okay, so that's kind of just in general, just to have an idea about that. Line regenerative braking captures the energy produced by the decelerating motor and sends it back to the system. Dynamic braking dissipates heat while regenerative braking recycles the energy. Okay, so the big difference between the two, again, with these terms, just concentrate on the differences as much as what they're actually doing. DC injection braking, another way of providing braking power at low speeds is by injecting a DC voltage onto the motor stator windings, producing a steady flux. The rotor spinning in the field produces a torque in the opposite direction from the rotor rotation and stops the rotor. Some VFDs have both dynamic and DC injection braking. Dynamic braking offers braking for deceleration, and the DC injection braking is used for final stopping. Okay, so you do a combination of both to potentially take advantage of the best braking for any situation. So definitely have a read through that. It's not too terrible. I mean, it's a lot of information on VFDs. We did talk about this in third year, but definitely read through, go through, make sure you do the objective exercises and get through the blackboard, and you'll have your doubt.